today's class, we will try to talk about what is called as a total derivative, and we will try to see why is a total derivative relevant for understanding motion in atmosphere. So, in the last lecture, we were trying to see what is the equation of motion, the generalized equation of motion, which accommodates all the forces. So, which was something like this: dV by dt is minus 1 by rho del p plus g star minus plus nu del square u minus 2 omega cross u plus omega square r. What is omega square r? Omega square r is the centrifugal force, right. We have seen what all these forces are. Now, I will tell you one very important aspect of this force. So, G star is, what is this? This is called as the true gravity. True gravity. What is true gravity? So, we know that any object on the center on the surface of the earth experiences a force towards the center, right. So, this force is called as the true gravity. True gravity always acts towards the center of earth or towards the center of mass of the planet, right. But more importantly or more interestingly, there is so the first reason is earth is not a sphere, right. So, we will try to see, let us say we imagine a quarter of the earth like this. So, this is the object, right. Now, as long as the earth is not revolving, there are no apparent forces. The only force that the object will experience is the true gravitational force, which is acting towards the center. But as the earth rotates, when things become non-inertial, so there is a constant non-zero force, which is omega square r, which is acting away from the axis of rotation, which is perpendicular to the axis of rotation, right. No, the effect of this force is that we have to add these forces. The vectorial sum of these forces will act or will appear to be in this direction, which is away from the center or slightly away from the center of the axis, right. So, if this is this becomes the radius of the earth, and this g, what you see, is called as the apparent gravity. Apparent gravity. So, this is because of the addition of centrifugal force to the true gravity. So, this apparent gravity will not act towards the center, rather slightly away from the center. So, a consequence of this force is that ideally you would expect the earth to be a perfect sphere like this, but over the period of time it so happened that the earth became something like this. So, there is a difference of equatorial radius and polar radius. So, because of this force, which is constantly acting away from the center, all the objects or the entire mass of the earth existing at higher latitudes will start to experience a force towards the or slightly away from the center of the mass. So, with time, over a period of time, it so happened that this force has continuously been pulling the object towards the equator. So, we now see the earth not to be in a perfect sphere, rather kind of in a bulged shape. So, that means that the equatorial radius being slightly larger than the radius at the poles, right. So, this is one very important aspect of true gravity and apparent gravity, and as a consequence what we can do is we can accommodate g star and omega square into g itself. So, our equation of motion will now become dV over dt is minus 1 by rho del p plus g plus minus 2 omega cross u. So, plus nu del square u. So, this equation is called as the Navier-Stokes equation, or this equation is the momentum equation, which tries to write the acceleration as this sum equal to the sum of forces. So, we do not write the centrifugal force separately. So, from here onwards g, the effective gravity or the apparent gravity takes care of the centrifugal force addition into the true gravity. But the only thing very important that you should remember is, you always remember the true gravity to be acting towards the center of mass and the apparent gravity to be acting away from the center of mass, slightly away, right. And what is the consequence? The consequence is that we have the equatorial bulge of the atmosphere of the earth itself, right. Now, here one very important aspect is about the air parcel. What is an air parcel? Air parcel. So, what is an air parcel? So, like I said before, we cannot apply the equations of motion, we cannot apply the laws of thermodynamics, we cannot apply the laws of fluid dynamics over the entire volume of atmosphere. We will have to take this infinitesimally small possible volume of air, and then we will have to apply the equations on this. So, this is generally called as the control volume. Now, what becomes interesting is, this control volume moves from one point to another point. You write an equation for this. This equation is of course valid for the atmosphere itself, right. So, now how do you define things within this particular control volume? We define all the dynamical variables, the density, pressure, volume, temperature, etc. All these dynamical variables are defined for this control volume. What are these? These are called as the field variables. These are called as the field variables. The field variables and their derivatives, we have to assume that, number one, very important assumption is that the field variables and their derivatives are continuous functions of position and time, are continuous functions of x and position and time, right. Now, the equation that we have seen, this one should be able to explain the motion of atmosphere, no matter how small or how large. It can be anything, right. So, this equation should explain things like, let us say, what are the various types of motion. So typically, when you take a tornado, the typical scale of this particular motion is 10 to the power of 2 meters. And if you take a cumulonimbus cloud, the typical scale would be of the order of 10 to the power of 3 meters. Then you take a hurricane, the typical scale that we are talking about is 10 to the power of 5 meters. Then you take a synoptic cyclone, the scale is of the order of 10 to the power of 6 meters. And you take a planetary wave, the typical scale is of the order of 10 to the power of 7 meters. So, what I mean to say is, no matter what the equation, so if I call this equation as number 1, the momentum equation. So, number 1 is valid or should be able to explain all of these phenomena, not just one. Which terms become important or relevant is going to be a very lengthy discussion. We will of course discuss this aspect in subsequent classes anyway, right. Now, what we have to do is, if we have to understand, if we have to develop equation which is suitable for all these different types, then we have to remember a simple fact that the air parcel, which is the smallest representation of the atmosphere, should be treated as an entity by itself, and all the variables are defined within that particular air parcel. And if we have to write any equation, if we have to account for any change of this pressure, volume, temperature and density, we will have to have appropriate methods or appropriate equations. Right. Now, one very important aspect is to discuss this is to discuss the variation is in terms of introducing what is called as a total derivative. So, what is a total derivative? Now, let us say as long as the object is fixed at an x, and if you are trying to see how things change within that object, you can write you can write dou d by dt. But when this object or when this air parcel is moving from one point to another point, what may so happen is that the changes that are occurring inside the air parcel or the control volume may be due to the movement from one point to another point. So, what is happening as it goes? So, there is a convergence and there is a divergence of air into this volume. So, in order to account the change as following the motion. So, total derivative is a derivative which accounts change in a dependent variable with respect to independent variable, which accounts change following the motion. What exactly is following the motion? Change the, so these are x, y, z, t. These are the variables, right. So, you have to find how does the pressure change with respect to position, or if you want to find out what is the pressure change with respect to time. But if you are trying to find this as the parcel is moving from one point to another point, so that particular change or that particular derivative is called as the total derivative. So, let us assume a physical parameter capital T, which is the temperature. Now, we will say that the position is changing with respect to time, right. X is changing with respect to time, y is changing with respect to time, z is also changing with respect to time. So, that means temperature now will depend on x, y, z, t. So, if you imagine an air parcel sitting at the surface, its temperature is something, right. Now, if this air parcel is taken to a very high altitude, the temperature is something else. This temperature change is not because of what is happening inside. You have not compressed it or you have not expanded it, but the temperature change is just because it has moved from one point to another point. Due to the ambience, the temperature has changed. So, what is the change in temperature with respect to time? Of course, for the duration of time which has occurred between this point and that point, and also because of the change in x, y, z to a new set of values, right. So, this change if you account change in this particular way, that particular variation is given by a total derivative. So, total derivative is also called as the total derivative is a very important tool in order to in atmospheric dynamics. Total derivative, also known as a material derivative, which can also be called as, this is also called as a substantial derivative. The most important characteristic being it calculates the change following the motion. Now, the field variable that we have taken in order to understand this is temperature with respect to x, y, z and t, right. Now, let us say, so you start at x 0, y 0, z 0 and t, and after some time, so these variables become, these quantities become x 0 plus delta x, y 0 plus delta y, z 0 plus delta z, and time changes to delta t, t plus delta t. Now, we can write the change in temperature with respect to x, y and z to be equal to dou t over dou x, change in temperature with respect to x plus change in temperature with respect to y plus change in temperature with respect to z, delta z, plus dou t by dou t into delta t plus higher order terms, right. Or if you can, what you can do is we can write delta t with respect to time. If we divide with respect to with time, we have dou t by dou x into delta x by delta t plus dou t by dou y into delta y by delta t plus dou t by dou z into delta z by delta t plus dou t over delta t, right. Now, when the limit tends to 0, when the limit delta t tends to 0, we can write dou t over dou t as dt by dt. So, that means d capital T by dt is equals to dou t by dou x times u plus dou t by dou y times v plus dou t by dou z times w plus dou t by dou t. Or you can write it as dt by t is equals to. So, this one can be written as u dot del t plus dou t over dou t. So, this is what is called as the total derivative. So, what is one very important aspect about total derivative? It tries to give you change with respect to while following the motion, right. Now, when we have written the momentum equation, so this term is here, yeah, let me write it again. So, let me just for the sake of clarity. So, dt by dt is dou t by dou t plus u dot del u. So, this term is change with respect to only time. So, dou t by dou t is telling you the change only with respect to time, nothing else. But this term is called as the advection term. Advection term. So, easiest way to understand the advection term is if you take an air parcel from one point to another point, this term accounts for the change in the physical variable, change in the dynamical variable, just because the air is replaced by another air because of the movement, right. Now, ideally, since you are writing, if you have written the momentum equation, ideally the momentum equation should be written in terms of a total derivative, because you are trying to follow the motion, and you then, if the air parcel is moving from one point to another point, the movement is guided by the balance of these forces, right. So, you can write the momentum equation now with respect to the total derivative, as dv by dt is equals to dou v by dou t plus v dot del is now equals to minus 1 by rho del p plus g plus nu del square u minus 2 omega cross u. Okay. So, this was some detail about the total derivative. So, total derivative, what is the importance of total derivative? Total derivative simply tells you how the variation is included while following the motion. So, you have two terms here. One, so basically let us say if you look at it this way, if you have this system and you have temperature defined inside the system, what will you do? You will try to, generally we are accustomed to find out change, either is dou t, or we are accustomed to find the change with respect to time, right. But or let us say if this is moved from one point to another point, we are accustomed to find out what is the change with respect to position, right. Now, when you combine these two things, we are calling it as the total derivative. How the temperature changes as it is moved from one point to another point, and this movement is again taking some time. So, with respect to time plus with respect to the motion, with respect to systems change x y z to x 1 y 1 z 1. So, these two things combined are called as the total derivative. So, total derivative is generally written with d over dt, capital D over dt, right. So, this was some information about the total derivative. Now, like I said, the air parcel is a very crucial or the most fundamental block in understanding the atmospheric dynamics. How does it work out? The air parcel can move from one point to another point. The air parcel can also be called as the control volume. So, the control volume, depending on the type of system that we are trying to understand, control volumes can be of two different types. Number one, that control volume can be a Lagrangian control volume. Then the control volume can also be a Eulerian control volume. So, what is the difference? What is the difference between the control volume? Two different types of control volumes. One, the Lagrangian control volume is, let us say the Lagrangian control volume is something, a smallest volume which moves from one point to another point. So, if you consider the fluid, the element of fluid that you identify as the control volume is kind of moving with the fluid, right. So, it is not fixed with respect to time. So, that means its position and time change as it moves, but the Eulerian control volume is not like that. The Eulerian control volume is fixed with respect to the axis. Let us say if this is the Eulerian control volume, this remains fixed, but the fluid instead moves or flows through this control volume, right. Now, so this is some basic information about the control volumes. Why I am telling you the information about the control volume is that, so far what we have done by discussing or by understanding the types of forces, we have not gone into the full mathematical derivation of the forces. We have directly picked up the force per unit mass expression from those derivations, the last expression from those derivations, and we were able to write the equation of motion. So, number one aspect is this equation of motion is sufficient to tell you how air moves from one point to another point as a function of time. Fine. The second important aspect is when you are trying to describe the motion of atmosphere, there are three things that you need to conserve. Then number one, you need to conserve the force, you need to conserve the mass, then you need to conserve the energy. Okay. The force conservation, when you have written the force conservation itself, right, you have accounted all the forces on the right hand side, you have made a sum, then you said this sum should be equal to the net acceleration per unit mass. So, this force conservation has given you what is called as the momentum equation. Fine. The mass conservation on the other hand will give you what is called as the continuity equation. The energy conservation on the other hand will give you what is called as the thermodynamic energy equation, right. So far we have seen how the conservation of force will work out. So, now what we will do is we will try to write this momentum equation in the full spherical polar coordinates. We will try to write it in its fullest form, then we will try to understand will we be able to solve the equation, and we will realize that we will not be able to solve this equation, then we will try to see what is the roundabout, or how do you make this equation useful, things like that, right. So, we have seen how we can conserve the force and obtain the momentum equation. then we will try to see how the mass can be conserved to give the continuity equation. Then finally, we will talk about the energy conservation, which gives you the thermodynamic energy equations. So basically, this set of equations are called as the governing equations. We will try to derive all of those equations and then try to see how we can solve it or how we can use this equation to explain anything in the atmosphere. Okay.